So now we will take up problems concerned with the first ordered high pass filter as well as the second ordered high pass filter. Okay, so 7.5 is obtain frequency response data similar to the table in 7.3 for the first ordered high pass filter at a cutoff frequency 400 Hz and a passband gain of 1. So as soon as you see the passband gain of 1, all throughout, if you see, we are using in the filters only the figure, any figure if you see, it's always the input is given to plus. That just means that it's a non-inverting amplifier. Non-inverting amplifier will have a passband gain of 1 plus RF by R1. So if 1 plus RF by R1 is equal to 1, then RF by R1 will be 0. That is, RF will be equal to 0. We can't choose R1 equal to infinity. There's no meaning in that. But RF equal to 0. And might be, you can choose both of them also. RF is equal to 0 and R1 equal to infinity. And that itself will give us a, if this is infinity and this is 0, then naturally we have a, so to say, voltage follower. Okay, we have the voltage follower circuit, right? So as soon as you see the gain is equal to 1, then you should assume that you are following a voltage follower with RF equal to 0 and R1 equal to infinity. That means there is no RF, and RF, R1 is definitely not connected at all. It's open, just means that we are not connecting, R1 and RF. In place of RF, you have a short circuit. RF equal to 0. 0 will be corresponding to short circuit. Infinity of resistance will correspond to a open circuit. So just remove R1 and RF should be shorted. Okay, that is what, in place of a RF you will have short, in place of R1 we will have an open. That is the case of the passband gain equal to 1. That's the first point. The second point is the high pass filter over here, which we briefly discussed in the last class also, wherein we said that the gain will be corresponding to this, that is V0 by Vin is equal to AF F by FL divided by root of 1 plus F by FL whole square. Or otherwise, if you take this down, as I said, right, then this will become 1 by F by FL will become, F by FL, if you take it within the root, it will become square, and naturally 1 by F by FL whole square will be equal to FL square by L, and this will be F by FL whole square divided by F by FL whole square, that will be 1. So it will be effectively 1 plus FL by L, FL by F whole square. 1 plus FL by F whole square with the root and whatever AF value will be there. So either you write this or you can write that also. Okay. So it all depends upon FL and FH, both are same, 1 by 2 pi RC. This will be the cutoff frequency. This is not going to change. Okay. And this AF is equal to 1 plus RF by R1 was also not going to change for the first order filter. Okay. So both these are not going to change. Only earlier we had here AF by 1 plus F by FH whole square. Now what we have is AF into F by FL divided by root of 1 plus F by FL whole square, or AF divided by root of 1 plus FL by F whole square. Either of the two you can use the formulas. Fine. So you just need to substitute that and try to do that. Right. So for that, already I have told you, if the way in which to do that would be F is equal to 1 by 2 pi RC, and you need to choose the value of the C, right, and choose the value of F, right. If F is given to us, because F is given to us over here, 400 Hertz, choose the value of C. C might be anywhere less than 1 microfarad, might be you'll choose 0.01 microfarad. So if you use 0.01 microfarad with 400 Hertz value as the frequency FL, what will be the value of R? That we need to find out. Okay. And if it is nearer to the standard value, you can choose the standard value itself. Or if it is not nearer, then you can choose a part, okay, which can be varied and fixed according to that value, so that we get the proper, cutoff frequency. Okay, proper cutoff frequency. So as far as passband gain is concerned, as is mentioned over here, the passband gain is concerned, AF will be equal to 1 plus RF by R1, and naturally we will get 1 1 cancelled, and RF will be equal to 0, and R1 will be equal to infinity. Okay, either way you can try to write that. So that finishes the job, or you can just say that for a passband gain equal to 1, we'll be using the voltage follower circuit. Okay, voltage follower circuit. So having written that, then he is also telling us to plot. Okay, write the table, and also might be to plot. Okay, his frequency response is similar to table, and he is not asking here plot, but okay, once you know the table, you can use the plot also. So table 7.3 is what he's talking about. It's just the same procedure. Above the cutoff frequency and below the cutoff frequencies, you take some frequencies and try to write the plot. So cutoff frequency is 400 for us, which is somewhere here. So take from, say, 10, 50, or might be 10, 20, 100, 200, 400, and then might be 1,000, 2,000, then 10,000, 20,000, then might be 1 lakh, and all that, whatever values you want. Okay, start from might be 10 over here when we are using cutoff frequency as 400. Okay, it's up to you, right? But however, the value at 400 will be, because cutoff frequency is 400, the value at 400 will be naturally the value, the value which will be 1.414 of that value, or rather 0.707 of the 2 value. Okay, 2 value. Because sorry, we have the AF equal to 1, so that's rather important, right? Since AF is equal to 1, you should use that value of 1. So naturally, in that particular case, when we have the value equal to AF equal to 1, that should be used, not the value 2. Okay, so AF will be equal to 1 is what is given to us, and hence corresponding to that, we will have the substitution over there. Okay, in the formula. So AF will be equal to 1. AF by FL, whatever you want to write. FL is given to us 400. FL is given to us 400. Okay, for different values of F, you can find out this total value, assuming naturally, because passband is given as passband gain is given as 1, and that value should be used there. So whatever passband gain is asked, we should use corresponding to that, right? So for the high pass filter, for very high frequencies, the passband gain will be equal to 1, and for low frequencies it will be 0. For the cutoff frequency, it will be 0.707 of the maximum value. Maximum value here is 1. Okay, in other case it might be a little different. Okay, so I think that makes sense. Okay, so we'll go for 7.6 in the circuit of figure 7.8, right? C2 equal to C3 equal to 0.047 microfarad, R2 equal to R3 equal to 3.3 kilo ohms, R1 equal to 27 kilo ohms, RF is equal to 15.8 kilo ohms. Determine the low cutoff frequency FL of the filter. Obtain the frequency response data and draw the frequency response from the plot. So here we are not asking for the design, but rather we are asking for the frequency calculation, right? So this is C2, C3, R2, R3, R1, RF, all these things are given to us, and we need to find the corresponding what you call low frequency, low cutoff frequency FL, and also the frequency response data, and draw the frequency response. So naturally, because we have C2, C3, R2, R3, it should be a second ordered filter. 7.8 is the figure which corresponds to the high frequency, right? Okay, so you have resistors here and capacitor here. Whenever you have resistors here, then it will become a differentiator. A differentiator is definitely a high pass filter. Okay, when you have this capacitor here and resistor here, capacitor here and resistor here, two set of them, it is second order high pass filter. Okay, right? Second order high pass filter. So corresponding to that, we just need to see the formula for that. The what we call V0 by Vin is equal to AF divided by 1 plus FL by F, whole to the power 4. Please remember this, it's a second order. So therefore it will be FL by F whole to the power 4. Okay, where AF is 1.586. The passband gain for the second order Butterworth response. AF should be equal to 1.586. Okay, now we need to find out the F value there. So again, he has given determine the low frequency cutoff frequency FL of the filter shown in the figure 7.8A. So this value is given to us. Similar problem we have. Draw the frequency response of the plot. So 1 by 2 pi R2, R3, C2, C3. We know R2 equal to R3 and C2 equal to C3. In our problem also, okay, where it is given here, C2 equal to C3 equal to 0.047, R2 equal to R3 equal to 3.3 kilohertz. So you just need to substitute in this formula and get the value of FL. For the values given there in this figure, right, he has found the FL to be this much, but we might have some difference in the value. The frequency response data in the table 7.4 are obtained from the voltage gain magnitude equation 7.5, which is repeated here for convenience. V0 by Vin is equal to AF divided by 1 plus FL by F whole to the power 4. Okay, so AF should be equal to 1.586, he says, but is it really that? We need to find out from the values given, R1 and RF. So you can just write 1 plus RF by R1, 1 plus 15.8 kilo ohm by 27 kilo ohm. I think it will turn out to be that much only. Okay, it might turn out to be 1.586, which is the value, which is the standard, which is given there. Okay, only then it will act as a Butterworth filter. Otherwise, it will not act as a Butterworth filter if AF value is something other than 1.586. Okay, so that we need not bother, or even if we calculate, we'll get the same value. Now for that, we need to write the frequency response data and the frequency response plot for the filter. So that just means that we need to use this formula. Okay, 1.586 divided by 1 plus FL, whatever value you have calculated, that will become the center frequency, 1 by 2 pi, so to say, the value root of R2, R3, R4, R5, right? C2, C3. Okay, so that is 1 by 2 pi RC, it will be. Okay, second order, you should remember that over here, 1 by 2 pi RC. Okay, RC where again R2, R3 is equal to are same and C2, C3 are same. If they're different, you need to substitute differently and put the value of root there. Okay, so earlier also we had similar equation 1 by 2 pi RC. Here also we have similar equation. Okay, so now given this formula over here, right, center frequency, whatever we have calculated, above that and below that values you take and try to find the so to say the what you call table, and then the response table will be similar to whatever we have written over here. Okay, V0 by Vin and 20 log V0 by Vin. This value has to be plotted against this. This should be on a logarithmic plot, logarithmic scale. Okay, logarithmic scale. So that's the one which we should use there. Fine. Now let us go for the next problem, which is 7.7. Draw the schematic diagram for the fourth order. Fourth order is out of the scope of our syllabus, because we have here first and second order, high pass, Butterworth, band pass, first order, low pass, high pass, Butterworth filters, band pass filter, band reject filter. Okay, so we don't have in our syllabus fourth order low pass Butterworth filter. Okay, that's not needed. Okay, then the following specifications are given for a certain wide band pass filter. FL equal to 400 hertz, FH equal to 1 kilohertz, pass band gain equal to 1, and calculate the value of Q for the filter. So band pass filter, we have it, only it is wide band pass, right? So correspondingly, let us see whether, what is the circuit for that and what are the formulas for that. Here we are given FL and FH because it's a band pass. Okay, so you have band pass means middle frequencies, will be passed. Okay, extreme frequencies, lower frequencies and higher frequencies will be cut off. Middle frequencies are passed. Band pass means within the band, the frequencies will be passed. Frequencies which are in the middle portion will be passed. Okay, whereas in the band stop, middle frequencies will be stopped and the lower and higher frequencies will be passed. Okay, so between FL and FH it will be pass band, and below FL and above FH it will be the stop band. So pass band gain is equal to 1. Pass band gain, as soon as you see equal to 1, one should remember that RF will be equal to RF will be equal to 0 and R1 equal to 1. That is just means that we have the voltage follower circuit, right? So he says calculate the value of Q for the filter. Okay, this I think might be, it will be similar to whatever we might have done in resonance also. Okay, might not be much difference. Let us see. Okay, so wide band pass, second order high pass is over. Higher order filter we don't have in our syllabus. Fourth order and all. Band pass filter. Okay, so Q is equal to FC by BW. Okay, FC by BW. FC is the center frequency divided by FH minus FL, right? FC is equal to root of FH into FL. Okay, so wide band pass, okay, will be formula will be this, where FC is equal to root of FH FL. So simple problem over here, nothing big over there. So what do we have? FC is equal to root of FL FH, 400 into 1 kilohertz, 400 hertz into 1000, so to say, hertz. So find that value of the root, whatever we get there. Okay, might be somewhere around 600 and odd. Okay, and 600 hertz and odd, because this is 1000 and this is 400 root of that. Then FC divided by FH minus FL will give us the value of Q. Okay, so only Q is asked. Calculate the value of Q for the filter. So very simple problem. You just need to substitute over here. In place of FC, you write root of FH FL divided by FH minus FL. So FH is given, FL is given, find the value. Okay, so next we will go for the next problem. 7.9. A certain narrow band pass filter has been designed to meet the following specifications: FC equal to 2 kilohertz, Q equal to 20, AF equal to 10. What modifications are necessary in the filter circuit to change the center frequency FC to 1 kilohertz? FC was 2 kilohertz, now it becomes 1 kilohertz. So what modifications should you do? Keeping the gain and the bandwidth constant. Differentiate between this wide and narrow. Wide band pass filter means the bandwidth will be very wide, 400 to 1 kilohertz. Whereas here he's telling you narrow band pass means very small region. Generally narrow, very narrow will be known as a notch filter. Very narrow means it will pass only single frequency. Okay, that will be known as a notch filter, N-O-T-C-H, notch filter. But otherwise narrow means might be 2 hertz, 3 hertz, 4 hertz, might be 10 hertz bandwidth. Here the bandwidth will be 400 to 1 kilohertz will give you somewhere around 600. Here it might be just 1 to 10 hertz as the band, bandwidth. Okay, very low bandwidth. And that can also be found by, we know very well that, Q is equal to FC by BW. Okay, Q is equal to FC by BW, or BW is equal to FC by Q. So BW can always be found 2 kilohertz by 20. That will give you 100. Okay, so even 100 he's telling us to be considered to be a narrow band pass. Okay, relatively we don't know what it means. FC by Q here turns out to be the bandwidth, and that is just 100. Okay, so AF is equal to 10. What modifications are necessary? Okay, in the filter circuit to change the center frequency FC to 1 kilohertz, keeping the gain and bandwidth constant. So we need to design. Design generally means that we need to find the value of R and C. Okay, so let us take, so wide band is over, we need to go for the narrow band. Okay, so this is wide band. Okay, same formulas we have. Narrow band, let us see. Okay, narrow band. Right. So narrow band filter is, shown in figure 7.13. 7.13 is here. Yes. So this is the narrow band filter, right? This is the narrow band filter. Our formula is given for the value of each one of this. We'll go for the straight, design. Okay. Choose the value of C1, C2 first, and then calculate the value of R1, R2, and R3 from the equation 7.11 through 7.13. Okay. So we need to choose the value of C1, C2. Might be we should choose one less than 1 microfarad. So you choose 0.01, whatever the frequency. Choose the value of C to be lesser than 1 microfarad. So choose say 0.01. Then use the formula from 7.11 to 7.13. 7.11 is R1 equal to Q by 2 pi FCCAF. Okay. R2 is Q by 2 pi FCC multiplied by 2Q square minus AF. So all those values are given to us. Q is given, FC is given, right? So where is that value? Okay, here 7.9. FC is given, Q is given, AF is given. Okay, right? Once all these are given, you can just easily find out the value of, R1, Q, 2 pi FC, C, AF. Okay, Q, 2 pi FC, C, AF. So all those values are given to us. FC is given, Q is given, AF is given. Okay. C is to be assumed, okay, which is the value which we have taken it as 0.01. Similarly, here again, C is assumed, the knowns are Q, FC, and AF, substitute there and get the value. R3 is Q pi FCC, so Q is given, C is chosen, and hence we can find R3, right? So then AF is equal to R3 by 2R1, AF is equal to R3 by 2R1, whether will satisfy this condition or not. Okay, we can check that. Okay, that's not necessary also because that's not asked. Okay, so here these are the values given to us. Same thing similar to that is what is given to us. Change this center frequency to 1.5 kilohertz, keeping AF and the bandwidth constant. Okay, so again it's a similar thing over there. We are changing the frequency here from 2 to 1 kilohertz, right? It is 2 kilohertz here and it is reducing to 1 kilohertz here. So there also it will be, the value which is whatever we have got over here, FC equal to 1 kilohertz to 1.5. Here there's an increase, there it is a decrease. That's all. Okay. So having found these values over here, right, we can choose the nearest values again, otherwise you should use PART. Okay, here is use 5.97, he's using here 6.2. R1 is 4.77, is choosing 4.7 because that's the available one. Here it is 95.5, so it's chosen 100 kiloohms. Now with these values, you can try to find out what are the exact frequency which is generated also if you want, but otherwise you can just leave it. Okay. Then using the equation 7.15, the value of R2 dash is to be calculated so that these cutoff frequency increases from 1 to 1.5. Okay, so R2 dash will be equal to the value of R2, 7.15. Okay. R2 dash will be equal to R2 multiplied by FC by FC dash whole square. FC is the old frequency, FC dash is the new frequency. Okay. So 2 by 1 whole square into R2. R2 we have found from here, and we just change this here. R2 dash is equal to whatever R2 we have got. F by FC whole square will become the value which is 2 by 1 whole square, that will be 4. So 4 into R2 will be the value of R2 dash. That's the only change we should make, okay, to get the center frequency, which is 1 kilohertz. Okay, FC dash is 2 kilohertz. FC is FC is 2 kilohertz, and FC dash is 1 kilohertz. Okay, so new value of FC is FC dash. Okay, 2 by 1. So, but in the problem which is solution which is given there, okay, it's the reverse, 1 above and 1.5 below. So naturally resistor value is decreasing. In our case, we are increasing the frequency. Therefore, the value, decreasing the frequency, hence the value of R2 dash is going to decrease. Okay, so is there any